When you've been looking at physics-based papers, specifically probably particle physics-based paper, you may have seen these strange, squiggly, line-based diagrams. You might have been wondering, what are these things? I don't understand what they are. I don't understand what they mean. Well, today we're going to talk about them, and I'm going to give you the basics of Feynman diagrams. Feynman diagrams are a basic representation of particle physics-based phenomenon that can occur, such as decays, scattering, and more. They were developed by this man here, Richard Feynman, as a useful way to visualize the processes and can also be deconstructed into getting the matrix element that can be used for calculating important features of these processes, such as the cross-section, or more specifically and in a less scientific term, the probability or the production rate of these phenomena occurring. So for example, if we were to have a particle that was going to decay into two particles, what is the likelihood that it will decay into those two specific particles? So now that you have a basic idea of what a Feynman diagram is, what do all the lines mean? Well, each of the lines is supposed to represent different particles and their interactions, or the forces that are causing interactions. In basic common Feynman diagram nomenclature, you have the fermions, or the 1/2 spin particles, which are represented by straight lines with an arrow. Now, they can either be starting at a point and pointing out from the point, or pointing into a point if they're the initial or final states. These usually are like your quarks or your leptons, up, down, strange, charm, top, bottom. Perhaps I need to give a video sort of explaining what quarks are, but it can also be the leptons, like electrons, muons. And again, perhaps all these particles should be explained to you in a video on the Standard Model. Now, there are also antiparticles, which are inverse charged versions of these fermion particles. Now, an antiparticle can technically be any kind of particle with a flipped charge. That is where there's the opposite. So, for example, you could have an electron which is negatively charged, and then the antiparticle is usually called a positron, or an anti-electron, which has a positive charge. Everything else about the positron is the same. It has the same properties. These are drawn in Feynman diagrams by being the same but with the arrow pointing in the opposite direction. This is because antiparticles can kind of be represented as a particle moving backwards in time. Why does this mean backwards in time? Well, I'll explain a little bit later when I show you sort of the elements of the Feynman diagrams more closely. But what about those sort of squiggly lines? Well, if it has little loops, these are color-charged vector bosons, or more specifically, gluons. Gluons are bosons, or a single spin particle, that have color charge, and they are the strong force, or they mediate the strong force. These are the sort of things that keep the quarks bound together into protons. You also have the electroweak vector bosons. These are bosons that interact with the electromagnetic or weak force. There is the proton, which interacts with the electromagnetic force. There's a W boson, which can have a charge of plus or minus 1. This interacts with the weak force, but it also interacts with the electromagnetic force by having a charge. And then there are Z bosons. Z bosons interact with the weak force and don't have any charge. Finally, there are scalar bosons. There is only really one scalar boson currently, and that is the Higgs. It has no charge, and it's represented by this dotted line. So now that you have this information, you can go ahead and draw a Feynman diagram using these elements. But there are some important pieces you need to know. Let's take a look at this Feynman diagram. In this diagram, we have a muon and an antimuon coming together to produce a photon. That photon is then going to radiate out and then decay into an electron and a positron. When we read a Feynman diagram, from one side to the other is the progression of time. However, with Feynman diagrams, usually, but not always, you can inverse the the direction of time, and they are still valid. Now in this case we're going from muons to electrons with the production of that photon. And you'll notice that when we have arrows along the straight lines, they follow a same shape. You're not having two arrows pointing together. They are essentially one line of arrows through. And that is a rule of the Feynman diagram. You cannot have a muon and, You cannot have a muon and another muon intercepting or interacting. There has to be something in between to disconnect that line. Now, this is also true that these lines have to be fully connected. So, we could have, instead, our muon go down, interact with something in the corner here, and then this could be a muon or an electron, and then interact with something here and come out as an electron, and have our lines like this, with other electroweak vector bosons likely here interacting, and that would be a valid diagram. But we can't just have this line come in here, this muon come in, and then also have an electroweak vector boson here. You cannot have sort of this disconnected arrow line. So this is some of the basics. We can kind of break down the Feynman diagrams into two different types. You have the decays, which are essentially a subsection of this diagram. This is where you have a particle and then it turns into two others, or a 3-point intercept. But this whole diagram itself would be considered a scattering diagram. This is where we have particles coming in, two particles come in, interact, and then two particles come out on the other side. There are in fact different types of scattering diagrams that have different names, but that might be for another video. Alright, now that you have a concept of what Feynman diagrams are and some of the basics, let's go ahead and open up a tool and use a little bit of our inner Bob Ross to draw some Feynman diagrams. I've opened up this web page called aidenshawn.com/Feynman diagram, and it is a useful little Feynman diagram maker. So let's go ahead and make a Feynman diagram. Now it has a lot of different elements here, so we can sort of see what our lines are going to look like, see what we're going to generate, and then paint them on here. So let's go ahead and do something very basic. Now, I am interested in a number of different phenomenon, mainly sort of jet production at the LHC. So let's make something that has some jets. Let's go ahead and put a line from here to here. So this is going to be some sort of scalar. And then we're going to have another scalar of a similar type down here coming up. And I want to have at the end the production of probably a Z boson. So let's go ahead and label these. Now, you don't necessarily need to label Feynman diagrams, but it is good practice. Because if you were going to put this in a paper or in a diagram or anything, really, it's really important to have what you have coming in here labeled so that people know what you're drawing. Now, jets are this interesting phenomenon that we get where essentially you have a quark moving away from another set of quarks, and so there's a gluon that binds them together, and said gluon gets stretched and stretched and stretched, and as it gets stretched further and further apart, it ends up storing more and more energy until it is essentially better for it to split into two gluons and a pair of quark-antiquark and separate out. So essentially you get this one pair of quarks into two separate pairs of quarks. And this is called hadronization. And essentially what happens is those other quarks still have that sort of separating momentum, so they stretch and pull and pop into other pairs of quarks. And so you get a bunch of mesons, or I guess hadrons in general would be probably a better term. You get a bunch of these quark combinations moving in the same direction, and so you get sort of this big stream of particles. That's essentially what a jet is. So what we want is something like a quark coming in and a quark coming in and some quarks coming out. And these quarks technically would come from larger particles. At the LHC we use protons, and so these would be would be coming from protons. But let's go ahead and just draw in. And we want one of these and one of these. Alright, so how do we get the Z? Well, the Z interaction is going to namely come out of a few potential places. We could do this. This would be called electroweak vector boson fusion. Essentially, there are vector bosons, as we talked about before. These are essentially all the bosons that aren't the Higgs, but vector boson fusion is when two vector bosons merge together and you get a production. This could be a Higgs boson, this could be something else. So what we're going to do is we're going to do what I like to work on. So this will be two vector bosons merging together to go ahead and make our Z. So in this situation, they're going to be W's. So let's say we started with two up quarks. All right, the Z has no charge, which means we need to have a W boson come out of each. Oops, my bad. Let me undo one of these. They're not going to both be ups. So we have an up here. Now, an up quark has a charge of 2/3, and a down quark has a charge of -1/3. So, if we take away a charge of +1 from our up quark, it's going to turn into a down quark. It's just very much simple math. So we go from up to down, charge of +2/3 to -1/3. Because we've removed this, we have a conservation of charge here. Great. Want to conserve our charge here as well, so we need our other W boson to have a charge of -1. What's interesting is the W boson plus and W boson minus are essentially antiparticles to each other. So what we're getting here then needs to take away a charge of minus. So this is probably just going to be the inverse, I believe, if I remember correctly. So this will be essentially a D boson turning into a U, or a down turning into an up. And there we go, there's our Feynman diagram. Or if we wanted it to look nicer, we could straighten these lines out and it would look slim. Or we could just even cut off these other elements here on the side. So that's one Feynman diagram. Let's do something else. So we're going to clear. Let's imagine we have an electron. You know what, let's make it a muon. Let's make it a muon. So it's interesting. Undo. What's interesting about Feynman diagrams is we can include things like loop diagrams in here. So I'm going to show you a single loop that we can put in. Now, we have a, we said muon, so -1. And we want our muon to essentially keep existing. Muon to muon. There can be the production, we can have sort of loops, and these loops can be at sort of the intercept points, or they can be along the lines. So most of these don't actually even matter. Oh, no, I gotta undo that. I want to get the curve right. Well, essentially what we can do is we can have also sort of curves in... Ooh. That didn't work well. Undo. We'll try this one more time. Oh, of course. Okay, I do. So we did it right the first time. I did it right the first time. Yeah, we can have sort of... Alright, there we go. And then, ta-da! So we can have loops within the line here. So let's say this was our muon. -1 charge, and we want a muon at the end. Now what we could do is we could have sort of an internal radiation of a charge, and that could change what this was, but that doesn't really work here, right? The muon has a charge of -1. We'd need to have it radiate out two things to change it into a anti-muon, and there isn't really a neutral charge muon. And also this would essentially come down to the thing called lepton number conservation, which I'll bring in a moment. But for this diagram, to make this work, this has to be like a photon. So essentially what's happening is, in the process of this muon moving along, it radiates off a photon, maybe because it has so much energy, it's moving so quickly, but then that photon is going to re-interact with the muon, and it enters back in, and so we just sort of get this circle here. Not the most interesting diagram, I know, but now let's go back to our muon. Right? We want our muon to go this way. Right? What's going to happen is our muon is going to decay, and it's going to decay into something. So like I said, let's undo. Conservation of lepton number. So essentially, in the leptons, or with leptons, there is lepton conservation. This essentially boils down to each family of leptons has a lepton number. So there's electrons, muons, and tau. And each charged lepton, which are the electrons, muons, and taus, has a neutrino, which is a neutral, chargeless particle that is also a lepton, and it is associated with it. And so essentially what this boils down to is when leptons change, right, we have a conversion, you need to still have a conserved lepton number. Essentially, you need to conserve the number of muons and the number of electrons. So let's say you started with nothing, and you produce an electron. You need to have the same number of electrons, or of electron-like leptons. So it could be electrons or muons. So we started with nothing. We need to conserve our charge, so you would have an electron and a positron. The positron is the antiparticle, so it also has the anti-lepton number, and so the two of them go ahead and cancel each other out. That was not very well explained, but let's try and show it with this diagram. So we have our muon. Let me move this little guy. Let's move him over a bit. There we go. Right, so we have our muon. Muon's coming along, but it's going to radiate. Now, it's going to radiate something out that has a charge because we want to produce a pair of leptons here. Well, we have a charge of -1, so the only thing that we can really radiate out would be a W- boson, like this. Okay, so the W- is now radiated out. This has no charge, but we need to keep the number of muons around, and this is not an antiparticle, so this needs to turn into a muon neutrino, right? Muon lepton number is 1, 1, 1, and it's still 1 here. Great, but now we have a charge of -1 that has been produced here, and these need to sort of line up to each other. So what we would get is we're going to get an electron, right? Because we can't make it a positron, this is -1, and so that's going to be the particle, but now it needs an antiparticle, and that antiparticle needs to make it such that the lepton number of electrons is totally 0. So we're going to go back down here, and we get an anti-electron neutrino. There you go. So there's another Feynman diagram. Okay, so that's sort of the basics. We could, of course, talk about like box diagrams. You know what? Let's do a box diagram just for the sake of it. All right. So like I was saying, you can get you can sort of draw things like boxes too sometimes. So let's say we have. Let's undo that one. Get a diagram sort of like this. We have a particle coming in, a particle coming out, and there's some sort of interaction. Right? So these need to be antiparticles of each other. And we will do this. Yeah. Actually, let's make this even more complex. We'll do that in a moment. I want to make this go from there to there, here to here, and here to here. You can kind of see the joy of just drawing these. Sometimes when I get bored, when I'm working and I don't want to actually work, I just doodle some Feynman diagrams on the side. But let's make this more complicated. Let's add another particle here. Interacting. All right. So let's try to make this diagram work. I think I want to put a photon in the center here. These need to, of course, balance out. And since we're dealing with electroweak, it's kind of just easier for us to... Might be easier to just play around with leptons, right? So let's do... This is a positron. Oh, sorry, this is an electron. We want to have this process. And we'll just sort of we'll copy everything out on the other side. So we'll make it mirror, right? This is an electron. You can see this is one type of scattering sort of here, but then we've added more complications by turning it into a box, adding more layers to it. Electron to electron. Need to transfer that charge through. We don't necessarily need to. This could not, but let's do that. Let's transfer. Yeah. No. Let's just keep this all photons, right? The easy way would be. This is a photon. Actually, no. Yeah, let's do this properly. If we want the other ones to be positrons. Alright, so let's make you a positron and you a positron. What we need to do is we'll transfer a W minus boson from this side to this side. So there we go, we're transferring a negative charge. That's going to turn these into electron neutrinos. And then, oh, did I mess up? Did I mess up? Our lepton number is conserved. Yeah, lepton number is still conserved on this side, from each side. So yeah, these turn into those. And then these will interact with a W plus. So what we've got here now is essentially a box diagram of an electron and positron interacting. We're getting some W boson on the side, so they're radiating those out. Then we get a photon interaction, and then we get these again. Actually, the photon interaction should not be there in the middle. And I'll tell you why. Very simply. Shoot. Undo. Move. Can I? Anyways, the reason there should not be, I'm just going to draw a line through it. This center interaction shouldn't actually exist because these electron neutrinos are chargeless. They do not have a charge. And so they don't interact with the electromagnetic force. I'm pretty sure. If I'm wrong, that would be terrible. But this also technically, actually what I would do here, let me undo this. what would make this actually work would be, can I hide this? No, I can't. What would actually make this work would be a Z boson here. Let's do that. Can I move? I just want to move. No. Okay. This system isn't my favorite, but if we instead of a photon, we used a Z boson interacting, then these are going to also, we would have these essentially turn into their anti-electroneutrinos. Yeah, but then of course to do this we would shift this diagram out a little bit just to sort of make it more obvious time progression wise. That should be valid, and that should make this this sample work. You can see I didn't prepare these beforehand. But yeah, welcome to the wonderful world of Feynman diagrams. There's a lot of fun little things you can do. For example, we had a gluon. Gluon interacts with the quarks, so we could always go ahead and have this decay into like a quark-antiquark pair sort of thing. Like this, where we have an up or an anti-up, an up and an anti-up. So there's a lot of things you can draw and design, and of course you got to keep in mind the rules: conservation of mass, conservation of momentum, conservation of lepton number, etc. But let your inner physics Bob Ross run wild. And I hope you've learned something in this little video on the Feynman diagram. Thanks for watching.